Okay, girls, if you go to your concyclic, actually, if you go to your student, not student notes, to the smaller booklet with, what's the smaller booklet called, girls? Yeah, the circle geometry booklet with the terminology on the front. Just go to that one. We're turning to page 4 of that booklet, and it says concyclic points. Now, what are concyclic points? They are points, not are points. Concyclic points are points that lie on the circumference of a circle. Okay? So concyclic points are points that lie on the circumference of a circle. So if you've got a cyclic quadrilateral, then your quadrilateral 4 vertices are on the circle. So a cyclic quadrilateral is a figure whose 4 vertices are concyclic. Do you get it? So yes, we've got a cyclic quadrilateral, therefore, a cyclic quadrilateral's endpoints or vertices lie on the edge of a circle. Okay, now let's look at circle theorem number 9. Okay, all right. If we look at, for example, angle A up here and angle C, I can't get them to whole numbers, I'll try. Well, that's close enough. Look at angle A and angle C. So this little program here is actually calculating them for us now. Notice that angle A is roughly 90 and angle C is 90, and 90 plus 90 is 180. And if we look at these ones here, I'll just change some values, make them not the same. Like, I'll try and get 80. If one's 80, the other one should be 100. So that's our first theorem. That's as close as I can get. For example, roughly 80, 100. So circle theorem number 9 is that the opposite angles of a cyclic quadrilateral are supplementary. Are we okay with that? And the converse theorem is if the opposite angles of a quadrilateral are supplementary, then the quadrilateral is cyclic. So that's almost a proof. That converse theorem is actually a proof of how to prove that a quadrilateral is cyclic. Cyclic quadrilateral means its endpoints lie on the circle. Actually, I'll be doing that proof with you a bit later, all right? So girls, write those down. You might also write on your diagram, for example, so your diagram's got an X and a Y and a P and a Q. On your diagram, you would write X plus Y is 180 and P plus Q is 180. So if you can do that, please. Oops. Okay, someone has just asked that do you just need one opposite pair? Yes, you only need one opposite pair. For example, that's 100 there and this is 80. So that's 180. Because the angle sum of a quadrilateral is 360, then the other two would automatically also add up to 180. So you only need to prove one pair of opposite angles being supplementary. Okay? All right, we're going to go to circle theorem number 9. Whoopsie, number 10, and I'll pause this video if I can, and I'm having problems pausing because I can't get into. Okay, we're going to prove circle theorem 9 later. I'll actually send you a link. I'll just send you an email and you can prove that theorem tonight. Okay, we're now looking at circle theorem number 10, and that theorem is the exterior angle of a cyclic quadrilateral. Now, you've seen exterior angle of triangles before, so here's my cyclic quadrilateral, C, D, E, and I don't know why that's K, but it is. So the cyclic quadrilateral is C, D, E, K. Remember, if you extend one of the sides, then that blue angle there marked 94 is the exterior angle. Notice that it is equal to the interior opposite angle. So if you look at what's next to 94, it's the 86. That's the angle next to it. That's the interior angle, but the interior opposite one is up there, 94. And I'm going to change that interior opposite one to blue as well. Actually, you want blue? Make it orange. All right? So that 94 out there equals this orange 94 up there. So the theorem is the exterior angle of this quadrilateral, of a cyclic quadrilateral only, not a normal quadrilateral, just a cyclic quadrilateral. So the exterior angle of the cyclic quadrilateral is equal to the interior opposite angle. Okay? Now I'm going to drag the vertices around. Watch. Wait, that's not helping. This one. That's not helping either. Maybe this one. There you go. So can you see that? As I change the size, that exterior angle 83 equals the interior opposite. Okay? And I can change some others. We happy with that theorem? So girls, that's our theorem. You can also write the converse theorem that if the exterior angle of a quadrilateral is equal to the opposite interior angle, then the quadrilateral is cyclic. Now that is another way of proving that a quadrilateral is cyclic. Okay girls, so in circle geometry, sometimes you'll just have a quadrilateral with no circle, but no circle drawn. For example, that circle might be missing. Okay girls? So, like I said, in some questions, a circle may be missing and they may say to you, prove that this quadrilateral is cyclic. And you can say, well, the exterior angle of 71 equals the interior opposite angle. Therefore, you can say that C, D, E, F, E, K, sorry, that those points must lie on a circle. Therefore, the quadrilateral is cyclic. Okay? Okay, we're on page 5. And what we're doing here, you'll notice there are two, at the top of page 5, it says finding the centre of a circle. What I'm doing this demonstration here, and you will draw a similar thing in that first section that says finding the centre of a circle. You've got that blank circle. Don't do it yet until I'm finished. So we've got 3 points, A, B, C. So what I'm going to do here is I'm going to use the segment tool, and I've got to find it. There we go, segment between 2 points. So I'm going to use the segment tool to construct a triangle ABC. So I click my segment tool, and I'm clicking on A and B. See, it draws a line. And then I'll click from B to C, it draws a line. And from C to A, it draws a line. So I've done step 1, okay? Then I have to use the line bisector tool to bisect AB and BC. So I think it's this one, perpendicular bisector. So I click on A and B, and it does the perpendicular bisector. And then I click on B and C, and it does the perpendicular bisector. I might move point C down, out. Okay? Now, then it says, so I've done that. So, oh, okay, that's fine. So girls, the way you actually, if you've got 3 points A, B, C, you can actually find the circle that passes through those 3 points by doing the following. You construct the triangle ABC. You bisect 2 of the sides. And what you'll find, if I do bisect that third side AC, it will pass through that point in the middle. It will. And that actually will be the centre of the circle that passes through ABC. So I'm just going to show you that now. All right, it says select the circle tool, and then, this is the circle tool, I think. And then click on the intersection of the bisectors there. And then drag. And then click on one of the vertices of the triangle, C. Okay, can you see what I'll do? I'll do it in a different colour. See? So, I like using this. So click on one of the vertices of the triangle, which I did. Notice at that point of intersection E, and when I came out and drew a circle, that my circle passes through A, B and C. Okay, now, if I actually draw, I'm going to do the perpendicular bisector of AC. I'm going to do it now, just watching. And it should pass through E as well. I'm just doing that now, and it does. See that? So I don't actually have to do that last step if I don't want. But if I do that perpendicular bisector of AC, then it passes through E as well. So you only need the perpendicular bisector of 2 of the 2 intervals, okay? And you don't need to actually do the third one. But that will give you the centre of the circle. And then if you had, you don't have to do it. You're not going to be asked to get a compass and put the point there and go out like that. Yeah.
You know how you're bisecting the sides? What happens if you bisect the angles? Will it still work?
I don't think so. Depends on the type of triangle that it would be.
Yeah.
I don't think so. I'm not too sure, but I don't think so. Okay? All right, so we have just drawn a circle through 3 non-collinear points. What does non-collinear points? Yeah, 3 points that aren't in a straight line. You cannot do this for 3 points in a straight line. It won't work. You cannot draw a circle between 3 points that are in a straight line. But any 3 points that are not in a straight line, you can draw a circle through them. So the conclusion will be that the intersection of the perpendicular bisectors of the intervals joining 3 non-collinear points is the centre of the circle. So girls, if you look at Circle Theorem 3 diagram on page 5, you can see that you've got 3 vertices, A, B, C, and that M is the midpoint of side AB, that N is the midpoint of side AC, and that P is the midpoint of side BC. And they, OM, ON, and OP are perpendicular bisectors of those intervals, or of those segments, yep, or of those lines.
Is that a drawing of the finding of a...
Well, Circle Theorem 11, can you write next to it the intersection of the perpendicular bisectors of the intervals joining 3 non-collinear points is the centre of the circle. So that goes in Circle Theorem 3. In the diagram above Circle Theorem 11, in the diagram above that says finding the centre of a circle, you can just do what I did if you want, or whatever, just do the steps. Actually, yeah, you might want to write the steps. So put your 3 points on your diagram, construct triangle ABC. Yeah, maybe do that above. See all those red steps? Write them where it says finding the centre of a circle. And Circle Theorem 11, write that purple bit down there. Yes?
What if it was like a scalene triangle, like it was like really...
Oh, it's okay. It could be. I'm going to move these points now, if I can. Watch. So I'm going to change this. Look. Wait. So that's the perpendicular bisector of AB. That's the perpendicular bisector of AC. I'm now going to do the perpendicular bisector of BC. Watching. I think it's, yeah?
No, you haven't done AC.
Oh, I haven't done AC. Thank you. So AC. There we go. And it still gives you the centre of the circle. See, that's the centre of the circle with that radius. I mean, I can click on this circle and delete it. But I can draw a new circle. Oh, I'll put it back. So if I go circle with centre through point, I click on E and back on B, and that gives me the circle again. Okay? I'm pausing the video now. Okay, this is Circle Theorem number 12. Now, it says ABC, notice this point D is off the circle, all right? So I've got ABC are 3 points on a circle, and D is free to move either on or off the circle. Now I'm going to move A and B a bit closer together, all right? Now, if D lies on the same side as AB, see AB? Notice if D's here or D's on the opposite side. Can you see that? So if D lies on the same side of the line AB as what C does, under what condition will D also lie on the circle? So I'm going to bring D to the circle and tell me when D's on the circle, what happens?
It's the same as the other one.
It's the same as the other angle. Isn't that angles in the same segment? So girls, when that point D is not on the circle, I do not have angles in the same segment or angles at the circumference subtended by the same chord are equal. But when I move point D to the circle, I do get that theorem angles in the same segment or angles at the circumference subtended by the same chord AB or arc AB are equal. So this is another theorem for angles in the same. So let's say the diagram of the circle is not there. And if you have, for example, something that looks like this, but that 50 is not the same as that 63, then you know that A, B, C, D do not all lie on the same circle. But if I move D and put it on the circle, and if you see in a diagram and there's no circle drawn. So let's see, if you look at your worksheet, notice there's no circle drawn on your worksheet, Circle Theorem 12. Can you see that? Now, what I can do, I might be able to get rid of that circle. I'll just see if it lets me do it. No, it doesn't. So girls, as soon as that 63, that angle at D becomes the same as the angle at C, then A, B, D, C are concyclic points. Can you see that? They're cyclic. It's a so if D is not on the circle, then the angle at...
Miss, you can get rid of it. You just got rid of the other angle.
Oh, I did? Oh, it's all right. I'll just leave it. So girls, when D is on the circle, notice that angle ACB equals angle ADB. Now, if the circle was not there and you had the diagram like you do in Circle Theorem 12 on your sheet, if alpha equals beta on your sheet, then A, B, C, D are concyclic points, or they form a cyclic, those 4 points form a cyclic quadrilateral. Okay? So, girls, if I put D on the opposite side, look. Oh, I got rid of that other circle.
Yeah, because you tried to get one, but you clicked the other.
Wait, there it is. Okay, so when D is on the circle, you get the angles in the same segment theorem. Can you see that? So when D is off the circle, you don't get that those angles are the same, the red angle and the blue one. So I'm going to bring it down. Now notice if D is up there, it's the same, but if D is on the opposite side of AB, you don't get angles in the same. But what do you get? You get opposite angles of a cyclic quadrisupplementary, and if I pull it off the circle, it's not supplementary anymore. Do you see that? It has to be on the circle to be supplementary. Yes. So this is the theorem that I'm doing now. Girls, there are theorems where you have to prove that something is a cyclic quadrilateral. So next to Circle Theorem 12, can you write that this is a proof for a cyclic quadrilateral? And the proof and the theorem is the following. If an interval subtends equal angles at 2 points on the same side of it, so there's your interval AB. If it subtends equal angles, so both these angles are 63, on the same side of it, then the endpoints of the interval, if you can stop talking please, then the endpoints of the interval and these other 2 points here are concyclic. In other words, they form a cyclic quadrilateral. Okay, girls? Now this is the converse theorem about angles in the same segment. Or this is the converse theorem of angles at the circumference subtended by the same chord are equal. It's the converse. It's saying if the two angles formed by that, if the two angles subtended by that chord are equal, then those points A, B, D, C are concyclic, or those points form a cyclic quadrilateral. Okay? The interval AB, for example. So I can do that. Oh no, I can't get to it. So you can write if the interval AB subtends equal angles at 2 points on the same side of it, then the endpoints, then you can say then ABDC form a cyclic quadrilateral or are concyclic. We say cyclic quadrilateral or concyclic points. Points are concyclic and the quadrilateral is cyclic. Okay? Okay, we're now going to work through pages 17 through to 21 of the booklet, and if you're not here, someone will send you those solutions, okay?